Hi, I'm Mr. Sand, and this is a walkthrough of a problem, which is Puzzler 2, problem number 3, I believe it is, where it says a person starts running with a constant velocity, trying to catch. Here, I'll just show it to you right here. There it is. It's very awkwardly phrased. I'll start off saying that. It's very awkwardly phrased. It's awkwardly phrased because I want to, for one thing, just make you think of sig figs, and another thing is, well, it's kind of a mistake. Part A really should have been kind of embedded in part B because you don't know what the strategy is for solving any problem because it doesn't ask you any problem until part B. So I'm going to do that. I'm going to look at part B and then use that to really answer part A. So just to start off here, you've got the paper in front of you, so I'm not going to read through that. I'm just going to set it up the right way. Okay. Shoot. There we go. Okay. So you've got this person, just a person that is, I'll just draw a picture first. They start from, they're running, and they're running with a constant, the velocity that they have, the velocity of the person is constant. Also, I'll just write constant. And they start off running 20 meters away from a streetcar. So a streetcar, I guess this is like in San Francisco, because that's the only place I really know of streetcars. So they're kind of like this, I guess. And there's a door in front. Okay, so it's a little streetcar, 20 meters away. The velocity the person is starting with is well, it's constant. We don't know what it is yet. The acceleration of that person is 0 meters per second squared. They're not accelerating at all. They're just going with a constant velocity. The streetcar, though, the streetcar is a little bit different. The streetcar, I'll make it look a little maroon-like. The streetcar is right here. So the velocity, the initial velocity, let's do the initial velocity of this guy, of this streetcar, is 0 meters per second, right? And the acceleration of the streetcar, I'll use C instead of S. The little subscripts, by the way, those just denote the velocity of what. So this is the velocity of the person, that's the acceleration of the person, this is the acceleration of the car, the streetcar, and this is the initial velocity of the streetcar. They give you this value right here, it's 0.9 meters per second squared. All right. So that's all the information that's given to you. I want to think about this in terms of a graph right now. So if I'm going to look at this in terms of the graph, I'm going to look at position versus time. So position would be on this axis. Position in terms of meters. And, oh, it's a little bit too big. I need space. Position. And then time right here. Time for seconds. And for the person's got a constant velocity. I don't know what it is. It's going to be a straight line here for a position versus time graph. So let's say that they start off at 0. That's our origin. And they're just going to run with a constant velocity. It's a straight line. But the streetcar does not start at 0. The streetcar starts 20 meters away. And it starts to speed up. It starts from 0. It starts at 0 velocity. So it would be a flat line right here if it was the instantaneous velocity. And it starts to speed up. So its slope gets bigger and 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 bigger. Okay, that should be like a curvy line. I didn't really draw that all that well for a curve, so it should be something like this, a curvy line. Okay, I'll do it one more time. One more time, like that, sort of. All right. The first question is, how long did the person run as soon as they... So the person goes right in it, like they jump onto the back of this streetcar. So we want to know how long the person ran so that we want to know the time it takes for this person to catch up with the streetcar. So in our little graph right here, that time it takes is at this time right here. As soon as this person this line right here, the position right here, equals the position of where the person is and the car is. That's the point at which they meet. So we've got 2 points. One, this is the time, this change in time right here, this delta t, is something I'm going to call this t catch. That's the time at which the person catches. Okay, that's the time at which the person catches the streetcar. And there's a position right here, which I'm going to call S catch. Okay, that's the change. That's a delta t, change of position that the person's had to go through. And the cars also, the streetcars also gone a total from that origin of that distance right here. So they both meet at that position at which they catch each other. Okay, so how long did the person run? That's the first question. Now, for a question like this, I don't expect you to know how to do this. Believe me, this is the first time you've seen equations that are anything that are just a little bit more complicated than like very simple equations. So we're going to use lots of manipulation here of these equations that are not so simple to begin with, and we're going to be doing lots of plugging in. So I just want you to follow the algebra here. This is actually a good precursor to some complicated acceleration algebra that we're going to be jumping into soon. So I don't expect you to take these leaps yourself. I just want you to try to follow my logic here. If you can follow my logic, then that's all I want. I just want you to say, oh, okay, that makes sense. If you can do that, then the battle is won. Okay? I don't expect, there will be nothing like this on the test. Believe me, I can ask one tiny part of this and it would be like a question on the test. One single step of this and it would be that'd be an entire question on the test. I'm not going to ask you this whole question, okay? It's way too hard. Okay, so I'm just going to write down some formulas that we're going to be using, and then we're going to be manipulating them, and we're going to be plugging things in and so forth. So here are some equations I'm going to make in blue. These are equations that are from, really they're from the next section in your workbook. So this whole problem is a little bit unfair if you got this in the first section of Unit 2. You can answer the first 2 questions pretty easily, but the last question is, this question right here is almost impossible. You need to know this equation, which is the position, the change in position of something. I'm just going to write down here the change of position for the car. Okay, the car equals, it's going to be 1/2 the acceleration of the car, delta t squared. And there is no initial velocity of this, so the units, the equation that we use, which is u delta t right here, that term drops out because there is no initial velocity. But to find the final position of this car, it does make sense. I hope you realize this. It does make sense to add the initial position to this. So the initial position of this is 20 meters. So this 20 meters is going to be sticking with us the whole time. Okay, so that's one equation that we'll be using. Another equation that we're going to be using is that the change in velocity of the car, equals the acceleration of the car times delta t. Okay, and we got this equation, at least you should remember this, I hope you do. The acceleration is delta v over delta t. Okay, we just rearranged that to get this equation right here for the car. See how I did that? I just multiplied both sides by delta t. And you get this equation right here for the car. We're just putting a car right here because we're going to use those in a second. Okay, again, I don't expect you to be able just to pull this out of the blue. It seems like I'm pulling it out of the blue right now, but there is a logic behind this. I just want you to follow what I'm doing. Okay. The last equation that we're going to be using is the delta s of the person. I'll substitute that with a p soon, equals delta v of the person Again, I'll substitute that with a p soon, and times delta t, or t time, delta t. Okay, and then we're going to consider the scenario at, I'll use this a different color here, at the time, at t catch. Okay, at t catch, which is this delta t right here, at t catch, we have a couple things that are true. At t catch, we have a couple things that are true. First thing that's true is that the velocity of the car is the same as the velocity of the person. And you should see that right here. This line, this velocity, the instantaneous velocity of the car is the same as the person. So they're exactly the same velocity. Another thing that's true is that the position, the delta t, or the delta s right here, so when I'm saying delta s, what I really mean is s catch. So the delta s of the person, delta s of the person, is the same as the delta s of the car. Okay. Right. So what I'm going to do right now is I'm just going to consider the scenario when they are catching each other, the time at which they're catching each other. I'm really concerned at that point. That's a moment of truth, really. So at that point, the delta t is just t catch. So what I can do is I can, instead of having delta t right here, I can just have the t, a time. And the same thing for velocity. The change in velocity, we're just talking about a point in time here, so it's going to be a velocity instead of delta v. So I just don't want you to be confused here that these deltas are going to be dropping off, because I'm just considered at the velocity at that time point, and I'm concerned with the position at that time point too, so that delta s is going to drop off just to be s, the position, and the time is also just going to be t instead of the delta. So we're going to lose all our deltas here, just because we're not talking about the change in time, we're not talking about the change in position, we're just talking about the overall position here, we're just talking about the time right here, that time, okay? So it is delta t, it is delta s. I'm just not going to talk about it in terms of delta t and delta s and delta v. I'm just going to talk about it in terms of v.